Hello everyone. What we have been doing is we are just trying to understand what is direct stiffness method and how it can be applied to different problems. We have already done it for truss analysis, we have already done it for beam, and today we will be applying direct stiffness method for frame. The main difference between the major difference between the frame and the beam and of course truss is, you see, truss we only have axial deformation, whereas in beam there is no axial deformation. The deformations we had is the rotation and then transverse displacement. Okay. Now frame, just combine, we have all the degrees of freedom. We have axial deformation, transverse displacement as well as rotation, and consequently the so at every point our degrees of freedom are 3, 2 translation and 1 rotation, and consequently the stiffness matrix, the size of the member stiffness matrix will also increase. Okay. So, the problem, before we start any problem, just quickly recall that if we this is the element stiffness matrix, right, for truss, and if you remember for this is for frame. For truss, if you remember, it was like this, only we had this part only we had, this part and this part. This is for the axial, this is the contribution from the axial deformation, and for this part and this is contribution from the transverse displacement and the rotation. So, this part for truss axial deformation, and this part we have already done for beam. So, essentially when you are talking about frame, it is combination of two. So, you have component of axial deformation same as truss, and then the component of transverse displacement and bending and rotation same as beam, and if we combine them, this is the element stiffness matrix for member stiffness matrix for frame, and the convention that is used here is like this. If you have any arbitrary member like this, see, unlike beam where your members are always horizontal, and therefore the sign convention, the convention that we used while deriving the stiffness matrix for member, and that convention remains same for all the member. But whereas in frame, whereas frame, we have members oriented in a different direction. We have horizontal member, vertical member, inclined at certain angle. Okay. So, that orientation also we need to consider. Okay. When we talk about this stiffness matrix here, that is obtained by assuming that the beam is like this. Okay. Your member is like this, horizontal. Okay. Now, the convention is, now suppose you take any member, we have discussed it, just we are reviewing that. Then this member is I, this joint is I, and this joint is J, and then degrees of freedoms are like this. This is first and this is second, and then rotation here it is 3, and similarly we have this is 4 and this is 5, and similarly rotation here is 6, total 6 degrees of freedom, and here also it is 1, 2, 3, 4, 5, 6, and it is 1, 2, 3, 4, 5, 6. Okay. Now, and then this is ith member, this is jth member, means this is any member, this is for any member m, this is for any member m, and this is node number I, this is node number j, and we are moving in this way. Okay. The element is represented as ij element. Okay. Now, then this is inclined at an angle theta. Suppose this angle is theta with horizontal, this angle is theta. Now, if this angle is theta, then this stiffness matrix as it is we cannot use. Then the stiffness matrix will become the K will become, suppose this is K dash, if we take, then K will be is equal to T transpose, T is the, and then K dash into T. T is the transformation matrix, which because of this orientation, change in orientation, the T takes care of that orientation. Okay. Now, again, if you recall that T is expressed, the transformation matrix is expressed as this. This is the transformation matrix that we have seen, where L and M components are. L is equal to, in this expression, L is equal to cos theta, and M is equal to sin theta. Okay. Now, then what we need to do first is, once we first take a member, and then represent the member by their corresponding node number and the degrees of freedom. This is the convention that we use, degrees of freedom, and we have to, if we are using this stiffness matrix in this form, this is the convention you have to use. But if you change the form, means suppose if we take this is 1, this is 2, and this is 3, then the same form you cannot use. Elements will be, what we have to do is, then we have to just the corresponding row and column we have to change, but the basic elements will be similar, will be same, but that row column will now interchange. Okay. Now, for this form, this is the matrix. Now, then once we identify the element, a member, we have to get this matrix, this is the K dash, and to get the element stiffness matrix, or the member stiffness matrix, this will be the member stiffness matrix. We know orientation of this member, and from this orientation calculate the transformation matrix, and then orient the stiffness matrix as per this orientation of the beam. You get the final stiffness matrix. Okay. Now, let us see, suppose consider this example. This is the example that we already solved using slope deflection method. Then also we discussed how to use it in using moment distribution method. Let us do it once again using direct stiffness method. Now, again, E cross section area, Young's modulus, and second moment of area, they are all constant for all the members. Okay. Now, let us start it. So, the problem is like this. Okay. This is horizontal, and then this is A, B, C, D, and then we have uniformly distributed load here, which is 7.5 kilonewton per meter, and in addition to that there is horizontal load 10 kilonewton. Okay. And then this is 10 meter, this is 5 meter, and this is 5 meter. The first step is write the member number and the node number, corresponding node number, and identify the degrees of freedom, corresponding degrees of freedom. Okay. So, suppose this is node number 1, this is node number 1, then node number 2 is this, node number 3 is this, and then this is node number 4. Okay. And the degrees of freedom are, this is 1, this is 2, and the rotation here is 3. And similarly, at node number 2, this is 4, this is 5, and then rotation here is 6. Node number 3, then this becomes 7, this is 8, and rotation becomes 9, and then at this point this become 10, then it is 11, and then rotation here is 12. So, we have total 12 degrees of freedom, but out of these 12 degrees of freedom, you see more 0.1 and 0.4 are constrained. So, we know that these values are 0, these degrees of freedom are D1, D2, D3, and D11, D12 and D10, they are 0. Okay. Now, once this is done, now let us we for member 1, we write this is member 1, this is member 1, this is member 2, and this is member 3. Okay. This is member 3, and suppose for member 1 we go from this direction, from this direction, means member 1 is 1 2, member is connected between 1 and 2. So, for member 1 point I becomes 1 and point 2 become yes, for member this is I the starting point and this is the end point. So, for member 1 the start point become 1 and say end point is 2. For member 2 it is 2 3, we go in this way, and for member 3 suppose we go this way. So, your start point becomes 3 and the end point becomes 4. Okay. This is very important, because if we are writing stiffness matrix in with some representation, and then the problem here is not only the stiffness matrix. Once you have that k dash, you have to transform it as well. Now, you write stiffness matrix in some orientation, considering in some orientation, and then transfer it in some orientation. That makes thing then that will be correct. Okay. Now, let us find out the stiffness matrices for different members. Let member 1. Now, the member 1, you see, remember this, when we write this stiffness matrix, when we write this transformation, then this transformation needs to be obtained like this, where theta is L and M is given by this, and theta is the angle with horizontal. Okay. Now, member 1 is your member 1, this angle is, if you measure from this, because this is the ith point, measure from it, this angle is theta is 90 degree, If theta is 90 degree, then L is equal to, which is cos theta, L becomes 0 and M becomes 1. Okay. Now, we know what is L, we know what is the value of L and M, we can get the transformation matrix from this, and then we know the properties of this member as well, length, Young's modulus, and second moment of area. We can get k dash from this, and once we have it, and then get the member stiffness matrix by this. Okay. So, next this, then getting the member stiffness matrix is again straightforward. Similarly, for member 2, member 2 is theta is 0, it is going in this direction, theta is 0. So, L becomes 1 and M becomes 0, again do the same thing. You see, if for member L, if L becomes 1, then M becomes 0. So, this becomes an unit matrix, right. So, all the elements are 0, on the diagonal elements are 1. So, it is same as when your transformation matrix like this, means essentially if you apply this, what you end up, you get k is equal to k dash. So, whatever your stiffness matrix k dash you obtain, after transformation also it will remain same, and that was same thing was happening for beam. So, beam, whatever stiffness matrix we had, that we use, we need not to transfer them, because your theta is 0 in that case. Okay. Now, so member 2 we can obtain. Similarly, for member 3, now member 3 is interesting. Member 3, you see, member 1 theta was 90 degree, but member 3, it is also oriented vertical direction, but theta is not 90 degree. Why theta is not 90 degree? Because our representation of this member from this to this. Okay. So, your angle become this is the angle. So, theta become 270 degree. Okay. This is now, if you consider the representation like this, from this point to this point, then you can take theta is equal to 90 degree. Okay. But since our representation is from this point to this point, your theta becomes 270 degree. So, this, please be careful with this is 270 degree, this convention. So, if it is 270 degree, L becomes 0 and M becomes minus 1. You see, in this case, though they are both are vertically oriented, in this case M is 1, in this case M is minus 1. Okay. Now, great. So, again we can calculate. So, we know what is we can, this will give us k1 and this will give us k2 and this will give us k3. So, we have element stiffness matrices. Once we have the element stiffness matrix, we have to assemble them. Again, assembling, the process of assembling we have discussed in the case of truss, we have also discussed in the case of beam. The process remains same. You write it in a different, suppose just for one example, suppose for member 2, okay, member 2, then this is, suppose this is your this is your element stiffness matrix, okay. Now member 2 is oriented like this, and corresponding degrees of freedoms are 4, 5, 6, 7, 8, 9. So this is 4, this is 5, this is 6, this is 7, this is 8, and this is 9, okay. So means it is for 4, 5, 6, 7, 8, 9. This is 4, 5, 6, 7, 8, and then 9. Similarly, you get for other two members as well. And then what you have to do? You have to, when you globalize it, you take element by element and then sum them and put that in the corresponding position in the matrix. Better way is when you actually writing when you were writing a code to disassembling. Better thing is, as we discussed in the truss, we know that in this case your global stiffness matrix will be, since you have 12 degrees of freedom, global stiffness matrix will be 12 by 12. You start with a matrix of 12 by 12, but all elements are 0, and then what you do, you just substitute and then keep on adding, at every position you keep on adding corresponding points from corresponding stiffness matrices, and then you get the global stiffness matrix. Okay. Now once you get the global, that exercise we are not doing it here, so please do that. So once we get the global stiffness matrix, next step is to get the load vector. Okay. Now again the process is again same. First we need to find out what are the fixed end reactions, and then we need to find out what is the corresponding equivalent joint load. Okay. Now first is considering these joints are fixed, and to get, so we assume that these joints are fixed, these joints are fixed, these joints are fixed, these joints are fixed, and on we have an uniformly distributed load here 7.5 kilonewton per meter, and then we also have 10 kilonewton load, right. Now what would be the equivalent? Then it is a fixed beam which subjected to uniformly distributed load. Equivalent, the fixed end moment will be WL square by 12, and then this will be this direction, this will be this direction. WL square by 12 become 62.5. Okay. I am not writing the unit here, otherwise things become very congested. Now then there will be a vertical reactions as well. This is, and this vertical reaction will be half of this, and this will be, this length is 10 meter. So total 75 by half, this will be 37.2, 37.5, and this will be 37.5. Okay. Now then there is no fixed end moment here, there is no moment here because there is no externally applied load here. So these moments and reactions all are 0. Now in this case, this load is acting at the joint. So it won't create any moment or any reaction to other joints. Only thing is there will be a reaction like this, which is 10. Okay. So this is the reactions if we consider this as fixed end, if we consider each member as fixed beam. Now let us find out. So this is for this, let us find out equivalent joint load. Equivalent joint load will be all the loads at this point and at this point, they all will be 0, right. So there is no equivalent joint load at this point and this point. This is node number 1, this is node number 2, node number 3, and this is node number 4. Okay. Now what is the equivalent joint load? Equivalent joint load here, equivalent joint load will be the total, if we sum them, whatever we get, just the opposite that. In order to if now when you consider them are fixed, whatever moments or reactions we get, if we sum them at the point, they won't be in equilibrium. So in order to satisfy the equilibrium, you have to apply just opposite moment or opposite force, that is the equivalent joint load. So, let us there is no moment here 1 and 4, there will be no equivalent joint load. Let us consider joint 2. Joint 2 horizontal direction we have 10, which is negative in this direction. So, there will be equivalent joint load will be a positive in this direction, which is 10. Okay. Now, then vertical direction a 37.5, which is upward direction. Then here also we have a 37.5, but there will be, it will be in downward direction. Then there is anti-clockwise moment of 62.5, there will be a clockwise moment of 62.5. So, this is equivalent joint load at node 2. Similarly, at node 3 there is a clockwise moment of 62.5. So, there will be an anti-clockwise moment of 62.5, and then a vertical direction 37.5, there will be downward direction 37.5. So, this is the equivalent equivalent joint load. And the next step is, once we have this, next step again we know that this is K into D is equal to Q. This is the stiffness relation, load displacement relation, and then we need to partition it. Partition it means those D which are known and those displacements, degrees of freedom, which are unknown. So, if we partition it, then after that we get K11, K12, K21 and K22, and the partitions are like this, which is now D unknown and then D known. Okay. And then this becomes Q known and then Q unknown. Okay. Now, what are the D's we know and what are the D's we do not know. So, let us do it here. Okay. So, what are the D's we know and what are the D's we do not know. Now, you see, at this point and at this point the reactions, all the displacements are 0. At this point we had these points we have D1, D2, D3 which are 0, and then D11, D12, D10 they are 0. So, only unknown D's are 4, 5, 6 and 7, 8, 9. So, D unknown are let us write it here, D unknown are D4, D5, D6, D7, D8 and D9, and all other D's are known and those are 0. Okay. And then what is Q unknown? So, let us write in a different page. So, D unknown is equal to D4, D5, D6, D7, D8 and then D9. Okay. D9, and then D known is equal to D1, D2, D3 which are at joint number 1, and then D10, D11, D12 which are at joint number 4. These are all 0. Okay. Now, similarly we need to find out Q known and Q unknown. Okay. Q known are what? These we know this Q known here. Okay. And what is Q known? Q known is, if you have to write Q known is equal to what? Now, you see we know these are supports, we know Q4, Q5, Q6, then Q7, Q8 and Q9. Okay. And so, Q4, Q5, Q6, Q7, Q8 and Q9 means these are at unconstrained, these Q's are the equivalent joint load at the unconstrained joint. Okay. And what are these values? These values are, you see, it is, this is Q3, Q4 is 10. So, this is 10, and then then we need to find out what is Q5 is minus 37.5 and Q6 is minus 62.5 minus 62.5 minus, because it is clockwise as per the sign convention for the stiffness matrix expression we use, anti-clockwise as positive, and then take Q4, 5, 6, Q7 is horizontal load at joint, which is 0 here, and then Q8 is this load, which is again minus 37.5 minus 37.5, and then finally Q9 is 62.5, which is anti-clockwise, that is why it is positive 62.5. Okay. So, this is Q known. Now, what we need to find out? We need to find out the, if we look at the partition, if we look at this partition, then this becomes this K11 D unknown plus K12 D known is equal to Q known, or in other way you can interpret that this degrees of freedom at unconstrained joint, degrees of freedom at constrained joint, and this is the equivalent joint load at unconstrained joint. Okay. Now, this is 0 that we have already obtained. So, K11 du is equal to Qk. So, from this expression we can calculate Qk. Okay. So, this will give us the unknown Q's. Now, once we know the unknown Q, then we need to find out this will give us unknown displacement. Now, then what we have to find out? We need to find out unknown Q. Then unknown Q will be again, then for that case we need to take the second part of this equation. Okay. This is the second part of this equation, which is K21 Qk, K22 K21 du, K22 dk is equal to Qu. So, Qu will be Q, but this will give us Qu, this will give us due to displacement, but total will be the displacement, whatever reactions you have because of the displacement plus whatever reactions you have because of this part, assuming this constraint. So, the total will be the fixed end constraint and plus displacement in this. So, total will be the Q assuming fixed, for fixed end, plus it will be K21 into D unknown. Okay. D known is constraint in 0, this will be the unknown reactions. Okay. Now, once you have the unknown reactions, take every element separately, apply you do the same procedure that we have already done for beam to get the forces in different members. Okay. So, this is how you can analyze frame. Now, the same concept with the demonstration is done using, we have demonstrated the concept using all the structure, the planar structure, but the same concept can be extended to space structure as well. For instance, if it is not plane frame, if it is a space frame, then what happens? The first is at every points, now we have 3 degrees of freedom. If you remember, the first week itself we discussed when in degrees of freedom, any point in a space we have 6 degrees of freedom, 6 to 3 translation and 3 rotation, and if it is plane, then we have 3 degrees of freedom, 2 translation and 1 rotation. And since all the structure we are trying to analyze here, these are planar structure, that is why for frame at every point we had 3 degrees of freedom. Now, if you have a space structure, at every point you have 6 degrees of freedom, and therefore, in any element we have any element connecting 2 points, the total degrees of freedom will be 12, 6 at ith point and 6 at jth point. So, element stiffness matrix, the member stiffness matrix will be 12 by 12 matrix. Okay. This is first difference, and the second difference will be, now when you orientation, in this case the orientation is still always in a plane, therefore, we had in the transformation matrix, we had just matrix can be represented by just one parameter theta. now in space frame, now the transformation is in 3D, in the orientation now is in 3D. So, your transformation matrix will be different, because then this transformation is to define with three theta's. Okay. So, your transformation matrix will be now different. Now, so similarly but the concept, once you have the transformation matrix, member stiffness matrix, then getting the element stiffness matrix for the actual orientation of the member, that step is same. Again, once you have the member stiffness matrix, then assembling process is again same. Once you have the assemble stiffness matrix, rest of the process is again same for even if you want to apply for 3D structure. Okay, but you see, direct stiffness method is what we have discussed in 1 week. It is just the purpose was to introduce direct stiffness matrix, because this week the direct stiffness matrix, this is the transition from your basic level structural analysis course, this course, and then slightly advanced structural analysis course. This is the transition from basic to slightly advanced structural analysis course. So, here the objective has been to introduce the method, but in order to understand the method, a full-fledged 1 semester or a half a semester course is required, and I believe that you will be having those courses in your subsequent semester. Okay. Now, this is the last class of the not last class. If we see from syllabus point of view, then yes, this is the last class of this course, but we will be having one more class where we try to summarize what we have learned and what we yet to learn. Okay, that we will be discussing in the next class, which is in a some way closure of this entire course. Okay, then I stop here today. See you in the next class. Thank you.